during some of the discussions, especially on characteristic function, we have seen that we can also find or have some idea about the moments of a distribution through the characteristic function, provided of course, moments exist, moments of a certain order must exist. So, the natural question is it possible to identify a distribution or identify a distribution or characterize a distribution uniquely through the moments if it exists. So, we will be discussing one important result in this relation in this area actually, but till now we are discussing that we can find a characteristic function or given a characteristic function and so on. Now, the basic question is how to identify a function as a characteristic function. That means, when can I say that given a function is actually a characteristic function. So, it must satisfy some properties, but it will be very interesting if it is possible to provide one theorem or one result that will give us some characterization or rather a necessary and sufficient condition for a function to be a characteristic function. Fortunately, we have one such theorem which is known as Bochner's theorem. Actually, this is one of my favorite theorems in probability and in characteristic function area. So, we will be discussing this Bochner's theorem in detail, and I will give you the proof, at least the outline of the proof, from which we have some idea that given a complex valued function, can we say that whether this is a characteristic function or not using Bochner's theorem. We know that a distribution function is characterized uniquely or determined uniquely by a characteristic function using inversion theorem. Now, when we are talking about distribution function, immediately the idea of moments comes into our mind. Now, you know that sometimes moments may not exist. So, whenever we are talking about moments, we will assume that moments exist or moments of a certain order exist. Otherwise, this discussion would be meaningless, or discussing about moments for a distribution function is meaningless unless it exists. So, the question is it possible to get the moments from the characteristic functions? We have already seen this thing. So, we are now going to discuss one important theorem that relates characteristic functions with the moments. So, as we have already seen, we know that moments may not exist, but a characteristic function always exists. But in case when there are some moments, that means moments of, suppose in a simplistic situation, suppose moments of all orders are finite, that means moments of all orders exist, then we can write phi t as an infinite series, that is 0 to infinity sum over j alpha j I t to the power j divided by j factorial for every t for which the right side converges. That means, this entire series, this is an infinite series. So, for all t for which this series converges, that is, and we know that this is a power series type of series. So, we can immediately say that mod t should be less than 1 by rho, where rho can be given as the lim sup of mod of alpha j by j factorial whole to the power 1 by j as j goes to infinity. So, this will give us some idea about for what range of t this series will converge. And we have seen many times that whenever we write phi t, we always try to see some of the properties like phi 0 equals to 1 and with some phi 0. So, phi t is defined at t equals to 0, which is immediately clear from this, that t equals to 0 is always there. Okay. Now, consider this theorem. If the series summation over j v j t to the power j by j factorial converges for some t naught greater than 0, then the sequence of alpha j determines the distribution function that is capital F uniquely. So, the question that I have already, the question with which I have started, that whether moments can determine a distribution function uniquely. So, that is answered by this theorem, provided this series is convergent. In particular, if rho equals to 0, then all moments are finite, and then the sequence of moments uniquely determines capital F x. Also, if lim sub of this, or upper limit lim sub is of V n to the power 1 by n is same as lim sub of alpha n to the power 1 by m by n equals to L, which is less than infinity, then the set of moments determine F uniquely. So, this gives a nice theorem under what conditions when the moments will determine a distribution function uniquely. Let us consider one example. Suppose a normal distribution, the well known normal distribution when x follows normal 0 1, we know that phi t equals to phi t, that is the characteristic function of this normal 0 1 variable, is e to the power minus t square by 2. Here alpha j, now you see we will not get any term involving odd power of t, because it is e to the power minus t square by 2. So, in every term we will get the power of t square. So, naturally power of odd power of t, the coefficient corresponding to that must be equals to 0. So, we can immediately say that alpha j equals to 0 if j is odd, and alpha 2j equals to 2j factorial by j factorial into 2 to the power j. Thus, we can write phi t as j equals to 0 to infinity minus 1 to the power j t square by 2 to the power j by j factorial, which is in fact e to the power minus t square by 2, which is less than infinity. That means, moments of all order exist for a normal distribution. So, we can say by virtue of the previous theorem that moments uniquely determine, this moments uniquely determine the normal distribution function. But now there is an example where let us define y to be a normal 0 1 variable and define another variable x, which is exponential of y, that is e to the power of y, and we know that this x, which is e to the power y, is nothing but a log normal random variable with some density small f x say, and if we calculate, if we evaluate this expectation of x to the power r, that is rth order moment of this x of the log normal variable, it will be e to the power r square by 2 for r greater than or equals to 1, r must be an integer. But we can, but it is observed that these are the moments, or exactly the same moments that can be obtained for a random variable whose density function is given by this, which is g x say c into f x. F x is the density function of log normal distribution into 1 plus half sine 2 pi k log x, where k is any integer and c is a normalizing constant. So, that the integration over the full range of x, that is 0 to infinity, g x should be equals to 1. So, that g x would be a PDF. So, here this cannot identify a distribution uniquely, because these conditions of the previous theorem are not satisfied. Now, the main question is, so we are dealing with characteristic function. Now, the question is, suppose I give you a function and I ask you that can you tell me whether this is a characteristic function or not? So, the basic most very important question is how to know whether a given function is a characteristic function or not. So, let us consider a very interesting theorem due to Polya. So, phi t is a real valued function defined for all real t, and it satisfies the 4 conditions actually. Phi of 0 equals to 1. I have just mentioned that phi 0 occurs many times in relation to characteristic function while discussing characteristic functions. So, phi 0 equals to 1, phi of minus t equals to phi t. Phi t is a third condition is phi t is a convex function for t greater than 0, and fourth condition is limit of phi t goes to infinity should be equals to 0. Now, it is clear that it is not possible that every characteristic function will satisfy these 4 conditions, because there is some kind of symmetry condition is there. So, there is a class of characteristic functions that might satisfy all these conditions, and if a function real valued, and remember this phi t is a real valued function. So, characteristic function might be a complex valued function. So, here we are dealing with a very special class of functions which are real valued functions and satisfy all these 4 conditions. Then this phi t, although it is a real valued function, is a characteristic function of an absolutely continuous distribution function capital F x. That means, since capital F x is absolutely continuous, so naturally we can get a PDF corresponding to this distribution function or corresponding to the random variable considered here. So, here we are getting a couple of interesting things. One is we are considering a real valued function. If it satisfies all these 4 conditions, this would be a characteristic function. So, this actually constitutes a class, a subclass of the characteristic function, or characterizes a subclass of characteristic functions. Moreover, this characteristic function has an additional feature that, or identifies an additional feature corresponding to the distribution function, which is that it must be absolutely continuous, which ensures that it will give us a proper probability density function corresponding to the random variable for which capital F is the distribution function. Let us consider some examples. So, these we call Polya type characteristic functions. So, if we consider small phi t equals to e to the power minus mod of t, we have seen that this is the characteristic function of a Cauchy distribution, and this is in L1, that means this function is integrable. If we consider phi t as 1 by 1 plus t, this is not integrable, this is not in L1, but it is still absolutely continuous. Again, consider one function phi t which is 1 minus t if 0 less than equals to t less than equals to half, and 1 by 4 mod t if t greater than equals to half. Not this characteristic function is not in L1, but it is again still absolutely continuous, because since it can be shown that this satisfies all the properties of a Polya characteristic function, all the 4 conditions, and hence this must be absolutely continuous. So, we can always get the probability density function corresponding to all these characteristic functions. Now, the question is, well, now we know that how to check whether a characteristic function, or rather whether a real valued function is a Polya type characteristic function or not. But this is not a very general result. So, now the question is it possible to propose or to prove one result or one theorem that will be much more general, that is general for any characteristic function? That means, can we provide some conditions which will characterize whether which will characterize a characteristic function? That means, given a function, maybe real valued, maybe complex valued, which I denote by phi t, can we propose couple of conditions which are necessary as well as sufficient? That means, for characteristic function, that means this should be a characteristic function if it satisfies these conditions. To this end, we have a very famous theorem that is called Bochner's theorem. This theorem actually provides a necessary and sufficient condition for a characteristic function. First, let us consider one definition, which is a complex valued function f t of a real variable t is said to be a non-negative definite, or commonly known as NND function, if first condition is f t is continuous, and second condition is for any positive integer capital N, any real number, a set of real numbers t1, t2, t capital N, and a set of complex numbers xi1, xi2, xi capital N, if we consider the sum of S, which is sum over j equals to 1 to capital N, sum over k equals to 1 to capital N, f of tj minus tk into xi j into xi k bar, that is complex conjugate of xi k, is real and non-negative. So, if we consider this sum, which is based on a set of real numbers, a set of complex numbers, and using the complex valued function f. But if we can show that this is real and non-negative, then we say that this complex valued function f t is actually a non-negative definite function, and this has a major role to play in the following theorem. So, Buckner's theorem says it is a very simple theorem. A complex valued function f t of a real variable t is a characteristic function if and only if, that means it provides necessary and sufficient condition if and only if number one condition f t is non-negative definite, and second condition, which is very simple, f 0 equals to 1. Now, I am not going to give you the detailed proof, but outline with some details at least how to prove this theorem. The necessity part is very trivial. If you consider this summation j equals to 1 to capital N, k equals to 1 to capital N, f of t j minus t k xi j xi k bar, and what is f t j minus t k? F is a characteristic function. So, I can immediately write this as expectation, that means integral minus infinity to infinity e to the power I of t j minus t k into x into d f x. Now, just changing the order of integral and summation, I can get sum of this into sum over k xi k e to the power minus I j k x, and integral with respect to the integral of the whole thing with respect to d f x, and we can immediately, it can be immediately shown that this quantity is nothing but modulus of sum of xi j e to the power I t j x whole square. Now, being this is the modulus of this function, this is always positive. So, this entire quantity is always positive, hence this function is non-negative, and so we can immediately say, and so the necessity part is proved. That means, given a characteristic function, this s, this sum is non-negative definite, and if we just put f t equals to 0, then f 0 equals to 1, that is already given as the condition. So, necessity part is proved. That means, given a characteristic function, we can always find this sum to be non-negative and f 0 equals to 1. Now comes the sufficiency part. Suppose f is, since f is non-negative definite, let us take h u as e to the power minus I u x minus u square sigma square. Then, if we consider this summation over j, sum over k, f of u j minus v k, h u j, h v k part, that is complex conjugate, and it is given that this is greater than or equals to 0. F is continuous, and for each x and sigma square greater than 0, as n goes to infinity, this entire summation sum tends to this integral, which is g x sigma, which we let us denote this by g x sigma, which is minus infinity to infinity integral of, again integral of minus infinity to infinity f of u minus v e to the power minus I into u minus v x minus x into u square plus v square into sigma square du dv. So, just by putting the expression of h u and h v bar in this expression and considering the limit as n goes to infinity, so that we can take this sum as the integral, we will get this expression. Now, here if we substitute t equals to u minus v and s equals to u plus v and integrate this thing with respect to s, then after a little bit of manipulation, it can be easily shown, it is very simple, that this is minus infinity to infinity f t by 2 pi, because if you put u minus v equals to t, we will get f t here, and e to the power minus I t x again from here, and from here we can say that this is minus t square sigma square by 2 dt, and naturally this is greater than or equals to 0. So, let us note one important thing, that if we consider 0 less than or equals to g x sigma e to the power minus x square beta square by 2, and if we denote this entire thing by h x beta, it is seen that this decreases in beta. This is a decreasing function in beta, and since this is decreasing, we can immediately apply monotone convergence theorem. to get integral minus infinity to infinity equals to limit, because we are taking the limit with respect to beta, because we are defining the sequence with respect to beta. So, as beta goes to 0, defining this function with respect to beta. So, beta goes to 0, integration minus infinity to infinity, this g x sigma e to the power minus beta square x square by 2, this function into dx is the limit of this entire quantity, just by substitution from the previous page. Now, again, since we have double integrals, we know by now that this is a very common technique to apply Fubini's theorem. So, just apply Fubini's theorem, and considering the fact that f is continuous, we have integration minus infinity to infinity g x sigma dx is this entire quantity. This is very easy to see, just little bit of simplification will provide you this entire expression. And just make one small substitution, t equals to u beta, then you will get this entire thing, limit of beta tends to 0 minus infinity to infinity f of u beta e to the power minus u square by 2 minus u square beta square sigma square by 2 into 1 by root over 2 pi du from the previous slide. And immediately we can observe that if beta goes to 0, then this becomes u beta goes to 0. So, f of u beta becomes f 0, and hence this is independent of u. So, it comes outside. If you again put beta equals to 0 in the exponent part, then u square beta square by sigma square u square beta square sigma square by 2 becomes 0. So, we are only left with e to the power minus u square by 2 divided by, so e to the power minus u square by 2 into 1 by root 2 pi du. Now, this quantity is nothing but the PDF of a standard normal variable, that is normal 0 1 variable. So, this whole, so we are basically integrating the PDF of a normal 0 1 variable, which is nothing but 1, and since f 0 is 1, so this entire integral becomes 1. So, what we get? We are getting integration minus infinity to infinity g of x sigma dx equals to 1. That means, this g of x sigma can be treated as a function of x, which is in fact the density of a distribution function, and we will show that this f t e to the power minus t square sigma square by 2, and hence the limit sigma goes to 0 of this function equals to nothing but f t is a characteristic function, definitely by continuity theorem. So, just integrating again with respect to x from minus infinity to infinity, and using Fubini's theorem, we will get minus infinity to infinity e to the power I tau x g x sigma dx equals to limit beta goes to 0 g x integration minus infinity to infinity g x sigma e to the power I tau x minus x square beta square by 2 into dx, and again applying the technique that we have used in the last page in just a few minutes back, and substituting this thing as t, substituting t equals to tau plus u beta, and a little bit of simplification, and applying this limit beta goes to 0, we end up with this expression f tau into e to the power minus tau square sigma square by 2. And another fact that we have to use every time, that normal characteristic function, the use of normal characteristic function. So, from here we are planning to, so initially we are planning to show that this would be a characteristic function, and hence if we take the limit of, that is f t into to the power minus t square sigma square by 2 would be a characteristic function, hence its limit as sigma goes to 0 would be a characteristic function. And we have proved that this entire expression f of tau e to the power minus tau square sigma square by 2 is nothing but integration minus infinity to infinity e to the power I tau x g x sigma dx. So, this is g x sigma is the PDF. So, this is nothing but the characteristic function of this random variable, and hence the proof. So, today we have learned, although we know that distribution function is characterized by characteristic function, or rather distribution function and characteristic function uniquely determine each other, but today also we have learned that whether a given function can be looked as a characteristic function or not, and the theorem in this direction that we discussed is the famous Bochner's theorem. So, now we have a tool, we have a result that will easily determine, easily guide us whether we can treat a function as a characteristic function. And if you remember the inversion theorem that we have discussed previously, that given a characteristic function, so first given any function, first check whether it is a characteristic function or not. Suppose it is a characteristic function, then we can derive the distribution function corresponding to that characteristic function uniquely through inversion theorem, and this distribution function will be unique. So, this together, all this theorem, we have an entire picture between the relationship between distribution function and characteristic function, how one can identify the other, how one can be determined from the other. So, these theorems are extremely important in probability theory.